This project really did start for me, well, not quite at the Google Faculty Summit 3 or 4 years ago, I don't exactly remember, but actually a couple of months before that when the then Vice Provost of Undergraduate Education at Stanford invited a group of us who had been award-winning faculty to come and talk about how we might change the way in which we teach at Stanford so as to open up more time in the curriculum for actual engagement between faculty members and students as opposed to just have a one-sided communication where the professor lectures in an auditorium for 300 students. And there were a bunch of us in the room and ideas were thrown around, nothing really clicked. And then a couple of months later I was not in this building, in another building, Google keeps expanding I guess, and listening to a talk about YouTube. And realized that it didn't really make sense for me to come into a room to give the same lecture that I'd been giving for 15 years, telling the same jokes at the same time, and then have that be the interaction that I have with the students. And the idea that came sort of almost full-fledged into my mind at that point in time was, why if we took that lecture and put it online, but in a much more engaging format? So a lot of the ideas that Peter mentioned that eventually ended up being part of this project were some of the initial ideas that came up at that point in time. The shorter video modules that were more focused on shorter, concrete, self-contained topics, so 8 to 12 minutes. The interaction within the video stream so that students are constantly questioned, and I'll show the example of in-video quizzes in a moment. The social interaction between the students around the material, which is so absent from today's classrooms, all of that was sort of part of the vision that I then went with to both Google, who graciously funded some of that initial effort, as well as to President John Hennessy, who gave an even larger amount of money. And then that basically led to the development of a lot of the ideas that ended up manifesting in these 3 Stanford online classes that Peter mentioned that went up in the fall of 2011. Now, at the same time, my colleague Andrew Ng, who was one of the people to offer these, one of these free online classes, came at it from the direction which ended up, I think, getting the bulk of the attention of this effort, which is the how do we get information to be, how do we get high quality course content to be available to everyone around the world for free? How do we change the dynamics? How do we change the world so that people everywhere around the world have access to the kind of education that currently is only available to a tiny sliver of the world's population who happen to be enrolled in institutions such as the ones where we teach? And so Andrew and I basically merged efforts a couple years ago. We ended up developing a lot of the ideas that, that made their way into this project, and I'll tell you a little bit about that today, although some of it will really echo some of the ideas that Peter already talked about, so I'll try and go through it a little bit fast. So first let me talk about the need. Maybe this is obvious to people, but the need for education is a really drastic thing right now around the world. And let me talk about 2 of the problems that maybe you're familiar with. The first is just lack of availability in large parts of the world to high quality education. One of the most poignant examples of that occurred in South Africa at the beginning of 2012, where the educational system in South Africa was geared for the white minority. And so there just aren't enough positions at the state universities to accommodate the much larger population that now wants and deserves a higher education. And so after the standard enrollment process at the University of Johannesburg had closed, there were a handful of positions left open. And there was a line of people a mile long outside the gate before they were going to open those positions, because of all those people who wanted to be first in line to get one of those slots. And when the gates opened in the morning, there was a stampede, and 20 people were injured and 1 woman died. She was the mother of a son, and she literally died to try and give her son a chance at a better life. Now, that of course is a real tragedy and is not that common, we hope, but the scarcity that underlies that is a real problem in many parts of the world. Closer to home, in the United States, we now haven't heard about this until recently. We've heard a lot about the rising cost of medical care. Everybody talks about that. What is less commonly known is that college tuition and fees have gone up at almost twice the rate. So since 1985 by about 559%. So that makes education unaffordable for a very large number of people, even here within the United States. So how do we use technology to help address some of those issues? And one way is by doing the 100,000 to 1, which we've already talked about. So in Andrew's class, he teaches machine learning at Stanford, one of the larger Stanford courses. It has 400 students every time it's offered. When Andrew taught machine learning to the general public, he had over 100,000 students. So if you think about that, in order to reach this size audience, Andrew would have had to teach his Stanford class for 250 years, which means he would get really bored by the end of it. So how do we exploit this power of 100,000 to 1? Well, it turns out that we can do that because once you take really great course content and put it out there for free, people keep coming in droves. Our current enrollment rate is about 30,000 students per day enrolling. We're now at 890,000 students from pretty much every country around the world. 2.3 million course enrollments, 116 courses from 16 universities. So there is a real need for this and people keep coming. But it's not just about the numbers. Individual people are really what it's about. And we get these amazing emails from people about how this type of course is changing their lives by giving them access to something that they would never have had access to before. And I can list hundreds of these, but I won't. Single mom of 2 teenage boys wanting to go back to school. There's hundreds of these that we could talk about. So what made these courses so different? I mean, MIT's OpenCourseWare has been around for a while. iTunes U, YouTube EDU, all of these are great resources. What made these so different? Why is this so impactful? Because this was a real course, and as Peter said, they did come up with the notion of deadlines. Deadlines turns out to be really important. So the course began on a given day, and then you can see the spikes. See the spikes in the traffic? That's the deadlines. Procrastination is truly a global phenomenon. And then the other thing is that at the end, the students got some kind of certificate, which we know they presented to employers. We know they presented to institutions at which they were enrolled students and actually got course credit for those. And so that is something that really gave them something of value for the effort that they put in. And that was the other thing that made this so impactful. Okay. So what are some of the elements that went into these courses? So the first is the personalization of learning, and we'll talk a lot about personalization in different points in this. So by breaking up the content into these little modules of 8 to 12 minutes, you can allow people to traverse the curriculum in different orders that better suit their learning needs. So you can have, for example, in addition to different trajectories through basic course content, you can have preparatory content that some students might need and others might not. You can have more advanced content that talks about specific topics that are of interest to some but not others. So basically, that allows you to move away from the one-size-fits-all of education that we've had to enforce in our students because of our need to scale up to 200 students who are sitting there in the auditorium. So personalization of the curriculum. The second, and this is one of the papers in addition to the Bloom paper, which I'll come back to, that had a lot of impact on me. This is a paper that talks about the importance of practice and constant practice in the learning format. So this is a paper that appeared in Science in 2011 by Karpik and Blunt. It's actually it's one of a long series of papers from this group and others. And what it shows are learning outcomes on the final exam by people who just studied the material, people who studied and reviewed the material, people who studied and did this exercise that cognitive psychologists really like called concept mapping about how these different things fit together, and people who studied and did a simple retrieval test after they studied the material. And even simple retrieval testing turns out to give a huge boost in performance scores, not just in memorization tests down the line, but also in conceptual tests down the line. And so this is a really valuable learning experience for the students in terms of improving learning outcomes. So where do we put in interaction and constant testing? And that's where we've put, I think, really the bulk of our efforts. So first, there is the interaction within the lecture itself. So these are the in-video quizzes, which was one of the things that I owe to the Google Faculty Summit a few years ago. So I'm not going to turn on the sound, but basically, if you heard the sound, this is Scott Page from Michigan. He's teaching. You can read the subtitles as he's talking. The video pauses. The student gets asked a question, submits the answer, gets told immediately that the answer is incorrect, tries again, and this time the student got it right. There's an optional explanation, and then the lecture moves on. Now, these are the kinds of simple questions that as an instructor, you or I might ask in class, but what happens when we ask a question in class? 80% of the students are still scribbling the last thing you said. There's that group in the back that's on Facebook. And then there's the smarty pants in the front row who answers the question before anyone else. That's Alfred. Thank you, Alfred. I was hoping it'd be Peter, but you know. And it's always the same guy or girl. And they answer the question before pretty much anyone else has even realized that a question had been asked, and then the lecture moves on. Here, every student is forced to engage with the material and has this retrieval practice opportunity. Now, of course, it's not about just these really simple assessments. In addition, there's real homeworks with real grades and real deadlines. We talked about that. So what kind of things so the question, of course, is if you have real homeworks, who's going to grade that? Who's going to grade the work of 100,000 students, right? We don't have 5,000 TAs. So at least Stanford didn't agree to fund it. I tried, but they refused. So what can you grade at scale? You can do multiple choice, obviously. You can do numerical answers. You could do short answers. You saw an example of that in the video a moment ago, using fairly simple text processing. You could do math, including mathematical expressions, graded in both syntactic as well as semantic equivalence. You could do programming and modeling assignments. I'll talk about that in a minute. And peer assessment is something that we recently tried out in order to allow grading at scale for the kinds of open-ended critical thinking work that is so central, for example, in the humanities, business, medicine, and others. So very briefly, on structured output, basically, that's the beauty of computer science, that you can actually grade meaningful work in a scalable way. So you can grade pretty much any programming language. You can grade some client-side, some server-side. JavaScript you can grade in the browser. It turns out that one of our faculty members is actually writing a Python interpreter in JavaScript so you could actually grade Python in the browser, which would be really cool. You could also do not just correctness testing using unit tests. You could also do more advanced assessments such as timing, memory use, test set performance. So for example, in my class, we had a spell checker from OCR data, and students were graded on how many spelling mistakes they've caught and corrected correctly. And so you could do all sorts of things like that. Now, programming is not just for us computer science geeks. Programming also comes up in the sciences and in the engineering disciplines when you want to write programs that are really models of physical systems, for example. Or, in some cases, models of things that are economic or social systems, like financial models or data analysis. Because you can grade Excel spreadsheets in the same type of structured output grading that you can programming assignments. So let me show you an example of. This is from the CS 101 course that Nick Parlante, who's also here at Google, teaches. The student's supposed to do color correction of that image on the right. They run it in the browser. It doesn't not quite right, so they get the chance to try again. I'll come back to trying again. It's part of mastery learning that Peter also mentioned. And then they basically are told that their output is correct and they can move on. So what about the humanities and the social sciences and so on and so forth? Open-ended work is something that also needs to be dealt with. And so that's where we adopted a pipeline. We merged ideas from two communities. One is the idea of calibrated peer review that education researchers and educators had used in small classes of 20 to 30 students. And the other is crowdsourcing, such as Amazon Mechanical Turk. And so by combining ideas from these, we basically put in a pipeline that allows you to grade open-ended work at a scale of tens of thousands of students. So first, let's talk about the education work. This is a paper from Sadler and Good, 2006, and it shows that peer grading, if carefully constructed, can actually correlate very nicely with teacher-assigned grades. So you can see a very nice correlation between teacher grade and the peer grades on the y-axis. What's even more interesting is if you incentivize students correctly to self-assess their own work, the correlation gets even better. So students are really good at assessing their own work. Since I'm out of time, I won't go into the details of the peer grading pipeline. I'm happy to answer questions about that. Let me briefly talk about the social aspects that Peter also mentioned. This is from the Princeton Sociology 101 class. Students decided to self-assemble on a map, showing where they are, and you can basically see the worldwide reach of this. And there's different formats in which students interact. So they interact with each other on the Q&A forum. And we use a Stack Overflow model, which unfortunately is cut off on the left, so you can't see it, but I'm sure you're all familiar with it, where students rank the questions up and down and rank the answers up and down. This is really critical for the kind of scalability. If you want the form to be usable for 100,000 students, it has to have that capability. It also has to have another capability that I'm not showing you, which is detection of semantically redundant questions, so that if a student types in a question that's already been asked, it automatically gets pulled up, and they basically realize that the question has been asked and avoid asking it, which reduces question fragmentation by an order of magnitude or more. People really thought that this was in fact a more interactive format than most face-to-face instruction. So this is an example of comment on the forum about how this was more interactive than non-virtual courses. Now, the other place where students interacted was actually in study groups. Students self-assembled into study groups. I'm actually going to show you the study groups for the Finance 101 class, for the finance class for Michigan that started out this week. There are 10 pages of study groups. Romania, Toronto, Indonesia, Greece, London, Vietnam. Basically, every country in the world is represented in these study groups, and some of them meet physically to just talk about the material. Others are purely virtual. Okay, back to this. So let me talk about some of the promises of this from a long-term perspective. First, there is the opportunity to really understand human learning. Human learning until now has been a study of hypothesis-driven work. People come up with a hypothesis, they construct a case control group of about 20 students in each group in most cases, and then they do the experiment. Here, we have unprecedented data. We collect every single click, where the student pauses, where they rewind, what they watch at 1.5x, what they submit as the first time they submit a question, what they submit the second time, what did they do in the middle. Every single thing is collected at a scale of 100,000 students or more. So let's think about what that can give you. Here is a distribution of wrong answers from one of Andrew's machine learning assignments. Answers happen to be pairs of numbers, so you can graph them on a two-dimensional plot. Every little x is a different wrong answer. So these are one-offs. The big x's are common wrong answers. So for example, that top left one is a place where 2,000 students submitted the exact same wrong answer. Now, if 2 students in a class of 100 submit the same wrong answer, you'd never notice. But if 2,000 students do the exact same thing, then it kind of jumps out at you. And so Andrew and his TAs went in, looked at some of those wrong answers, realized that the students had inverted 2 lines of an algorithm, and gave a targeted error message so that any other assignment that fell into that bucket, the student would get a tailored error message telling them what they ought to think about in order to correct their work. Personalization, once again. You could do more clever things than that. We've started to do some analytics. So here is the question of, if you submitted a wrong answer and then submitted a right answer to a problem set, what did you do in the middle? So you could ask that, for example, regarding form visits. So which form visits are the most helpful to move students from the wrong answer to the right answer? And you could formulate this as a probability of transitioning from wrong to right, and there is a formal way of doing that. And if you look at the ones that satisfy that criterion, you basically get the exact form questions that really help drill in on the misunderstandings that are most common. And so that can be used either to tell the instructor that they should have explained this better, or to tell the students that if they're struggling with this particular concept, they might want to go and look at this forum post, or in other cases, a video, and so on and so forth. So that brings us back to Peter's 2 sigma problem, a paper that was also influential for me. So I'm not going to talk about this very much because Peter already talked about the fact that the lecture is 1 achievement distribution, mastery learning is 1 standard deviation higher, and personalized instruction is 2 standard deviations higher. And so we get the Lake-Wobegon effect of 98% of students being above average. Now, the reason Bloom called this the 2 sigma problem is because we can't afford an individual human tutor for every student, but we can afford maybe a computer, at least a smartphone, for every student. And so the question is, how far can technology move us from the blue curve to the green curve? And mastery is actually easy because the computer doesn't get tired of showing you the same video 5 times or even grading the same assignment 5 times. And so we can get to the red curve. And some of the ideas on personalization that we're starting to play around with might move us closer to the green curve. Maybe not all the way, but maybe close enough that we can get some really meaningful improvement in learning outcomes. Do I have 1 minute? Okay. So, some of us might be thinking, oh my God, if this is so great, do we still need colleges, right? Do we still need universities, or are we all out of a job? And that's a criticism that's come up. Mark Twain certainly thought that we were redundant. But I disagree with Mark Twain. I want to go even further back to Plutarch, who said that the mind is not a vessel that needs filling, but wood that needs igniting. And maybe what we ought to be doing in our classes is something that is more igniting the minds, igniting the imaginations, teaching critical thinking skills. And basically, that comes back to the whole flipped classroom model, which was my original interest in this. And there's, again, a tremendous wealth of studies that show that when you do that, when you have active learning in the classroom, this is by Nobel Prize winning physicist Carl Wyman, who shows that when you compare lecture-based to active learning, you get an improvement of not 5%, but 30% in attendance, in engagement, and in learning. And we've been doing this in some of our Stanford classes, including my own, and I can tell you that these results hold up. Student engagement is up, student learning is improved, and I'm not going to go into the details of this because I'm out of time, but this is really the way in which we ought to go back to teaching, because lecturing, I think, is a thing that we ought to be moving away from and going back to teaching the way it should have been before we needed to scale. And I'll stop here.